Friend, let's set the day down together. Slip under the covers of a quieter universe, where the room feels warm, the night is kind, and nothing needs your attention except a soft breath in and a softer breath out. Tonight isn't a lecture. It's a gentle walk under distant light so your mind can loosen and your body can rest. Imagine your thoughts as little lanterns floating on a dark, peaceful sea. We'll nudge them along with calming truths about the cosmos, how space stretches like a slow tide, how ancient light still hums in the background, how the sky holds more stars than our worries could ever count. No rush, no memorizing, only the comfort that the universe is vast, steady, and quietly at work while you sleep. If this brings you ease, if these soft, starry ideas help you drift, feel free to like and subscribe so you can find this safe corner again whenever the night feels heavy. For now, let your shoulders sink, let the noise fall away, and let wonder arrive in small, drowsy waves. We'll begin when you're ready, slowly, calmly, together. And now, staying with that soft breath and the quiet that's beginning to gather around you, let's take the first slow step. Imagine we are lying back beneath a wide, dark sky, no rush, no schedules, just the hush of night and the patient shimmer above. As your shoulders loosen, let a single idea arrive. The universe holds more stars than every grain of sand on every beach on Earth. You can picture a handful of sand slipping through your fingers, each grain tiny and countless, and then magnify that to all the shores, all the deserts, all the hidden dunes. The sky outnumbers them. It isn't poetry. It's a calm, humbling scale. Each of those stars is not a pinhole or a spark on a black curtain, but a real sun-hot plasma held together by gravity, burning across distances so large that light itself must work for ages to cross them. Some stars are giants, swelling and cool. Others are tight and blue-white, fierce and quick-lived. Many are quiet, steady, middle-aged suns, not unlike our own. Around them may drift entire families, planets, moons, rings, dust worlds, with sunsets we'll never see and seasons we can only imagine. It's comforting to think that while we rest, countless little systems keep time, circling in silence. If you let your gaze soften over that imagined sky, you'll feel the vastness become a gentle background, a kind of cosmic lullaby. And still, even that sea of light is only the faintest surface of what we can know. There is a limit to how far we can look, a horizon set not by walls or fences, but by time itself. We call it the observable universe, a sphere around us about 90-something billion light-years across, the region from which light has managed to reach us since the universe first became transparent to it. Everything inside that sphere is close enough, in a cosmic sense, for light to have arrived. Everything beyond is still sending, still shining, but the messages have not yet had time to lodge in our eyes. This horizon is not an edge in the way the ocean meets the shore. Nothing stops there. Nothing turns around. It's more like the limit of your hearing when the wind is soft. Sound still travels farther, but you cannot bring it into focus. Beyond our horizon, space likely continues a calm continuation of the same tapestry, stitched with galaxies and clusters and long, delicate strands. We suspect this not because we've gone there, but because everything we do see obeys the same rules with remarkable consistency. The unknown flows outward not as a cliff, but as a widening of dark that is yet to send us its glow. The reason we have a horizon at all is that space is not standing still. it stretches. The distances between galaxies grow over time, not just because those galaxies are moving, but because the fabric that measures distance, the very grid of space, expands. If you need a picture, imagine ink dots on a balloon. As it inflates, the dots separate even though they don't crawl across the surface. No dot is the center. Every dot sees the others drift away. In that same slow way, the universe expands everywhere at once. The effect is gentle at a human scale. Your room doesn't swell, but across millions of light years, the stretch becomes the song that shapes the grand design. This expansion does more than set the tempo of distance. It also shapes what we can know. Light, traveling from faraway galaxies, rides a moving road. The wavelengths lengthen as the road stretches, sliding toward redder colors, toward cooler tones. Ancient light, on its way to us, arrives softened by that journey, a reminder that we are reading a moving book. When you look at a faint galaxy, you are not seeing it as it is, but as it was, the way a lullaby echoes after the singer has already left the room. Follow that thought further back, and you will arrive at a beginning that isn't an explosion in the ordinary sense. The Big Bang is not a fireball erupting in empty space. It is the event in which space and time themselves begin the first frame of the film, the starting pulse of the clock. Before that, there is no before in any simple way to imagine. There is no gap where you could stand and watch. In the earliest moments, the universe exists as something hot, dense, and quickly changing, then cooling and spreading as it grows. It is not fragments rushing outward into a pre-made room. It is the room itself, unfolding and filling, the stage building itself as the play begins. As the universe expands and cools, there comes a quiet, crucial moment when it releases its first light that can wander freely. Before that, the cosmos is too hot, too crowded with charged particles. Photons ricochet constantly, have no clear path, but as things calm, electrons settle into atoms, and light at last can travel. That light has never stopped. It is everywhere around us still, a faint glow now stretched into microwaves by billions of years of expansion. We call it the cosmic microwave background, and it is, in its way, the softest nightlight imaginable, the afterglow of the universe's early days, bathing all of space with a near uniform hush. Look closely at that hush, using instruments that can feel temperature differences smaller than a whisper, and you see that it is dappled, modeled by tiny variations. Those gentle speckles are not noise. They are the seeds of everything. Slightly denser patches in that ancient light grow over time into galaxies, clusters, and the filaments that thread them together. The universe is not a static grid. It is a story written in small ripples that amplify, a breathing pattern that organizes itself into stars and worlds and, eventually, beings who can wonder. In the quiet of your room, that idea can feel like a blanket, complexity blooming from the softest beginnings. And still, as bright as starlight is, much of the universe does not glow. There is matter that neither shines nor swallows light, matter that reveals itself only by gravity's tug. We call it dark matter, not because it is spooky, but because it is hidden to our eyes. It outweighs the visible stars and gas, forming a scaffold that holds galaxies together. Without it, the outer stars of a galaxy would whirl away. With it, they are gathered and kept. Telescopes map its presence not by seeing it directly, but by tracing its influence. How galaxies rotate, how clusters bend, the paths of light passing through them, how the large-scale pattern of cosmic structure grows over time. You can imagine dark matter like the quiet framework inside a lantern, unseen when the candle burns, but essential to the shape. It is everywhere, passing through us without ripple, threading the night beyond our rooftops, forming halos around galaxies. In this sense, the universe is not only a sea of light, it is a cathedral of gravity, arches and spans formed by what we cannot see, holding the luminous parts aloft. There is another presence, stranger still, that shapes how the story unfolds. In the late 20th century, astronomers expected the expansion of the universe to be slowing, gently held back by the mass of everything. Instead, the opposite revealed itself. The expansion is not just continuing, it is accelerating. The distances between galaxies grow faster and faster over time, as if space itself carries a quiet pressure that pushes outward. We call the cause dark energy, again a placeholder name, an admission that the phenomenon is known before its nature is understood. Dark energy acts like a soft, persistent wind in the fabric of space. It doesn't shove things the way a breeze pushes a leaf, but it changes the rules of the expansion, adding a faint, outward curve to the universe's history. What it is, exactly, remains among the deepest questions, a property of space, a field with steady energy, a shift in how gravity should be written. While we don't yet know, we can watch what it does, and what it does is make room, more and more room, between distant galaxies, rehearsing a future in which the very distant becomes the permanently out of reach. Hold that picture loosely and let it ease you. The universe grows not in chaos, but in a spacious, steady way. The stars teem, the early light whispers, the hidden framework gathers and supports. The expansion drifts, then drifts faster, not violently, but with a slow inevitability, like a tide that never turns. Through it all, gravity does its patient work. Matter clumps, gas cools, stars ignite, planets form. The story is grand, but the pace is gentle enough to fall asleep to. If you could step back farther, still far enough to see not just single galaxies, but how galaxies arrange themselves, you would find a pattern like lace. Astronomers call it the cosmic web, vast filaments of matter strung across hundreds of millions of light years, meeting at nodes where galaxy clusters gather, with enormous voids yawning between them. The luminous parts galaxies, with their stars and nebulae, trace out these filaments the way dew beads along a spider's thread. Dark matter supplies the thread, gravity draws the beads, and time adds the weight that makes structure settle. This web is not rushed. It took billions of years to take shape, drawn out by gravity's patience and the initial pattern of those tiny fluctuations in the ancient glow. As you picture it, those great strands, those deep, dark spaces between, let your breathing find the same rhythm. In, the thread draws. Out, the void opens. In the very largest view, the universe feels both intricate and calm, like frost flowers on a window pane, like ripples on a lake, stilled by evening. Pausing here, it's soothing to notice how each idea flowed from the last. The number of stars sets the scene, abundance beyond counting. The horizon reminds us that our vision is limited not by lack of curiosity, but by time's reach. Expansion explains why the horizon exists. and why light arrives in lowered tones. The beginning provides the first light, now stretched to a soft, all-sky murmur. Hidden matter holds the luminous islands together. Hidden energy urges space to widen. And over all of it, structure emerges delicate, spidery, inevitable. None of this asks anything hard of you tonight. You don't need to remember figures or proofs. Instead, you can simply let the shape of the story sink in. A universe that began hot and close, that cooled and opened, that seeded small variations and nurtured them into galaxies and webs, that hides most of its substance quietly, that floats on an expansion with a gentle, accelerating push. The facts are true, but their feeling is what matters here, the sense that reality is wide, ordered in its own soft way, and content to continue while you rest. As your eyes grow heavier, return once more to that first image. Sand slipping through your fingers, grains too many to count. Multiply them by beaches, then by worlds. Now, look up past your ceiling, past the roof, through the atmosphere, and imagine the sky answering with a greater number still. Each star a possible home, each home a candle you'll never need to tend. All of it keeps burning, distant and serene, without a demand on you. It will still be there in the morning. It will still be there a million mornings from now. So let the shore fade. Let the stars blur into a soft, milky fog. Feel the ground beneath you as part of a small planet, circling a quiet sun, tucked inside a galaxy threaded on a filament of a vaster web. All of it held together by forces that neither brag nor sleep. You are safe here, wrapped in scales too vast to be troubled by daily noise. In this calm, the universe feels not cold, but kind, immense, yes, and mysterious, but also simple in its patience. When you're ready, we can keep gliding to the first light that still hums around us, to the hidden matter that cradles the stars, to the soft pressure that opens space like a long exhale, and to the lacework that ties it all together. For now, rest inside the knowledge that the cosmos is both abundant and gentle, stretching quietly while your breath moves in small, regular tides. And as the room grows dimmer and your thoughts move like clouds, the next part of our journey will arrive as easily as sleep. Still resting in that wide, patient hush, let's draw the lens in just enough to notice our own neighborhood gliding through the grand design. The Milky Way is not a picture hung on a wall. It's a living spiral, a river of stars turning on itself with quiet determination. Our solar system rides that river at over 500,000 miles per hour, tucked inside an arm of dust and light, circling the galactic center like a small boat on a gentle but unstoppable current. One full loop takes about 250 million years, a single galactic year. In the time it takes to drift around once, continents shift, oceans rearrange their edges, and entire lineages of creatures rise and vanish. Yet in this moment, it feels wonderfully simple. Your breath, the dark, the soft spin of home. We move through fields of gas where new suns are born, past clusters where old suns take their bow, across lanes of interstellar dust that glow in faint, smoky ribbons. At these speeds, you might imagine danger. But the distances between stars are so immense that direct collisions are exceedingly rare. Mostly, we pass in silence like two snowflakes falling a mile apart in a windless night. Gravity holds the music together, but the stage is spacious. This is the kind of motion that soothes rather than startles, steady, continuous, confident. On much larger scales, galaxies sometimes find each other. They do not crash like cars. They drift together the way two fog banks mingle slowly, subtly, over billions of years. As they approach, gravity tugs on their shapes, stretches out tidal tails, and stirs their gas. The stirring awakens star birth in sudden bursts, as clouds are compressed and collapse. Stars themselves almost never strike one another, but the overall forms reweave. Spirals become ellipses. Disks grow thicker and smoother. Central black holes swell as gas funnels inward. Our own Milky Way and the Andromeda Galaxy are quietly committed to this future set to merge in about 4 billion years. From a safe vantage, it will be majestic. Arcs of stars, long streamers of debris, new regions of light. The two systems will eventually relax into a single, larger galaxy, sometimes nicknamed Milkomeda, a reminder that even on grand scales, endings are also forms of becoming. Far away so far that their light left in the universe's youth, some galactic hearts blaze like beacons. We call them quasars. At their centers sit supermassive black holes, not devouring space as monsters, but feeding, and in feeding, shining. As gas spirals into those deep wells, it heats to extraordinary temperatures and radiates across space, sometimes outshining the entire host galaxy. Think of a lighthouse in a very long night, its beam telling sailors not only where the tower stands, but what the coastline is like. In the same way, quasars light up the intergalactic medium and offer clues about the early cosmos, how quickly black holes grew, how matter was distributed, how the first big structures organized themselves. Their glow is ancient, but it still arrives, steady and crisp, like star song from a time when the universe was learning its first melodies. If you follow the trail of the story all the way back beyond the first galaxies, past the first stars, you meet a moment that changed everything in a fraction of a blink: cosmic inflation. Right after the Big Bang, the universe is thought to have expanded exponentially for an instant, with space itself stretching faster than the speed of light. That sounds like a rule broken, but it isn't. The light speed limit governs motion through space, not the growth of space itself. Inflation smooths the cosmos on large scales like smoothing a blanket with one long, even stroke, while at the same time magnifying tiny quantum jitters into the seeds that later become galaxies and clusters. The universe emerges from this event remarkably uniform, yet flecked with the faintest freckles, just enough to grow the intricate lace we see today. It is comforting to imagine that even the grandest patterns began as soft, small murmurs. After inflation's hush, and after the early heat begins to ease, there is a longer, deeper, quiet, hundreds of millions of years without a single star. The cosmos is dark, filled with neutral hydrogen that soaks up energetic light. Then the first stars ignite, massive, brief, brilliant candles that pierce the black. They burn hotter and faster than most stars today, forging the first heavier elements and blowing them into space when they die. Their fierce ultraviolet light reionizes the surrounding hydrogen, turning fog into clarity and making the universe transparent in a new way. This cosmic dawn is both delicate and dramatic, a thin scattering of lights widening into a city at night. The switch from darkness to glow is not a flip, it's a sunrise, seen from orbit, gradual, spreading, inevitable. From these lives and deaths come clues that still touch us. Every supernova sends out shock waves and, with them, a froth of cosmic rays, charged particles mostly protons and nuclei, accelerated to near light speed by stupendous electric and magnetic fields. They race through interstellar space, wander through the magnetic folds of our galaxy, and some reach Earth. When they strike atoms high in our atmosphere, they create showers of new particles that cascade downward, a kind of ghostly rain you can't feel. These visitors whisper of the power locked inside stellar explosions and black hole jets, connecting our small sky to the universe's most energetic events. They are rare enough to be harmless, common enough to be a quiet reminder. Distant storms still send ripples to our shores. Zoom out again, and you'll see that our Milky Way is not floating alone. It's one bright neighborhood in a far larger city. We belong to a sprawling region called the Laniakea Supercluster, immense heaven, a graceful flow of thousands of galaxies, loosely bound by gravity and moving together across hundreds of millions of light years. Imagine a continent of galaxies with rivers, filaments, and basins, clusters, all guided by the underlying terrain of dark matter. Within this continent, gravity steers motion, the way landscapes steer water. Paths curve toward deeper basins, tributaries join, eddies form. Knowing where our galaxy sits in this map helps us understand not just our local traffic, but the currents that shape the large-scale universe. Between those filaments and basins lie voids, vast stretches with very few galaxies at all. They are not perfectly empty, but their density is low, their light sparse. Paradoxically, these open spaces help define the web. Like the negative space in a drawing, they reveal the form by what is absent. Voids can span tens of millions of light years, and their presence influences how nearby galaxies move, how structures grow, and how we interpret the overall expansion. If the cosmic web is lace, the voids are the delicate holes that let the pattern breathe. There's comfort in that too. Even emptiness has a role, and the shape of nothing helps the shape of everything. Through all of this, a river of almost undetectable travelers runs straight through you, your room, the Earth itself, neutrinos. They are so small in mass and so shy in interaction that they pass through light years of matter as if through fog. Trillions stream through your body every second, most birthed in the sun's core, others forged in supernovae or particle collisions near black holes. To catch the rare interaction, scientists built immense, silent instruments far underground or beneath Antarctic ice, waiting for a single neutrino to leave a tiny mark. Each detection is a message from processes we cannot otherwise touch, a direct report from the heart of a star or from the collapse of a dying one. You can let that sink in. Even in stillness, you are crossed by news from the cosmos. And older still is another, even fainter sea, the cosmic neutrino background, a relic from just a heartbeat after the Big Bang. These neutrinos decoupled from the hot, dense soup of the early universe within the first second and have been gliding ever since, almost impossible to catch. Though we have not yet measured them directly the way we have measured the cosmic microwave background, their imprint appears in other observations and in the success of our models. They are the oldest travelers we know how to imagine, silent, almost non-existent in their touch, but significant enough to influence how structure formed. The universe, it turns out, holds a memory in particles as well as in light. Step back to the grandest perspective we can hold in a human mind, and something soothing appears. When we average over large enough distances, the universe looks uniform. No direction is special. No place is the privileged center. This isotropy and homogeneity simplify the story in a way that helps us sleep. The rules are the same everywhere, and the grand pattern is consistent. In this symmetry, there is a kind of kindness. It doesn't mean there are no local quirks, there are endless quirks, but the canvas behind them is even and calm. With that calm canvas, we can ask a quiet, practical question. How fast is the canvas stretching now? The answer lives in a number we call the Hubble constant, a measure linking how quickly distant galaxies recede to how far away they are. Like any good lullaby, the details are simple at first. Farther things recede faster. The line is roughly straight. But when we measure the slope very precisely, we find a small disagreement between methods: one, using the nearby universe, standard candles, and rulers; another reading the early universe's afterglow, and then forecasting forward. This tension doesn't keep the sky from turning. It invites refinement, better instruments, deeper understanding. It's a gentle puzzle placed at the edge of the bed, something to return to in daylight, not something to solve before sleep. Notice how these ideas arrange themselves, the way constellations make pictures from scattered stars. We began with motion close to home, our galaxy's steady turn, our long orbit around its center. We widened to the measured ballet of colliding galaxies, and the future embrace with Andromeda, a spectacle serene at human scales. We lifted our eyes to quasars, the brilliant hearts that outline the distant coastlines of the young cosmos. We walked back to inflation, where space unfurled too quickly to watch, smoothing the backdrop and planting the seeds of structure. We witnessed the first stars waking the universe, the dawn light chasing away the fog. We felt the small, swift messengers of violent events, cosmic rays arrive in our air. We traced our address in Laniakea, saw how voids defined the lace, sensed the neutrino river threading through us and the ancient neutrino sea surrounding us. Then we rested on the symmetry of the largest scales and the quiet question of the present expansion. If your eyes grow heavy, let them. Each fact is also a feeling. Motion without rush, power without threat, distance without loneliness. Our galaxy's speed is a cradle, not a chase. Galaxy mergers are slow embraces, not crashes. Quasars are lanterns in fog, not alarms. Inflation is a smoothing hand, not a storm. Cosmic dawn is sunrise, not a siren. Cosmic rays are distant fireworks, their embers too thin to scorch. Laniakea is a neighborhood map, not a maze. Voids are breathing spaces. Neutrinos are soft footfalls in a quiet hall. Isotropy is the room's even warmth. The Hubble constant is the slow tick of a clock you can barely hear. You can stay with any one of these images and let the rest drift to the edges. Imagine the Milky Way's spiral arms as rivers of starlight. Picture Andromeda's approach as two gliding swans circling closer. See a quasar as a pearl set deep in a velvet box, shining through the lid. Feel inflation as a blanket pulled smooth over a bed. Watch the first stars turn on like the far shoreline of a lake at night. Hear cosmic rays as a distant, unheard fizz. Hold Laniakea like a map folded gently in your lap. Let voids be the quiet rooms between words. Sense neutrinos as a breeze that moves through walls. And let the Hubble constant be the rate of your own breath steady, modest, enough. The night is still, and the universe is gentle company. When you're ready, we'll keep following the thread toward the light that lingers from the beginning. the hidden scaffolding that steadies the galaxies, and the patterns that knit everything into a single, calming whole. For now, rest in the knowledge that even at hundreds of thousands of miles per hour, you are not being hurled, you are being carried. And the carrier, the Milky Way, the web, the space itself, moves with a grace that asks nothing of you but sleep. Stay with the feeling of being carried, of motion that asks nothing from you. The farther those distant lanterns drift, the softer their glow arrives. That softening isn't a trick of your eyes. It's the universe telling us its pace. As space stretches, the light crossing, it stretches too, sliding toward longer, redder wavelengths. It's like the way a siren's pitch lowers as it glides away, only here the stage itself is moving. Each reddened note is a timestamp, a calm record of distance and time, letting us read how quickly the great fabric has been opening since the beginning. Because light changes this way, we can turn the sky into a quiet archive. Measure the redshift of a galaxy's light, and you learn not just that it's receding, but how far its message has traveled and how long ago it began that journey. The deeper the red, the older the whisper. Piece these measurements together across thousands of galaxies, and a history emerges. Expansion, slow at first, then guided by forces we're still learning to name, then gently accelerating. It's a lullaby written in color, each tone a step in time. To trust those steps, we need rulers that work across impossible distances, so astronomers build them one to the next, like placing stones in a stream. First comes parallax, watching the apparent shift of nearby stars as Earth moves around the sun, a tiny geometric wobble that yields true distances close to home. With those distances in hand, we calibrate standard candles, objects whose real brightness is known. Cepheid variable stars pulse with a rhythm tied to their luminosity. Count the tempo, and you know how bright they are, then how far. Farther out, certain supernovae flare with a characteristic light curve. Type Ia becoming beacons you can spot halfway across the map. Each method reaches farther than the last, and together, they form a cosmic distance ladder, a gentle, stepwise way to bridge the gap between our small yardsticks and the galaxy-scale seas. When the colors of redshift meet the steadiness of these candles, the picture sharpens, not a blur of lights, but a measured, breathing universe. Even with good rulers, our sight has a limit, not because anything blocks us, but because time itself is finite. Light needs time to arrive, and there hasn't been enough of it to deliver news from regions beyond a certain distance. That's our cosmic horizon, not an edge you could touch, but a boundary to what can presently be known. You can imagine it like fog beyond the lamplight. There is certainly more out there, and the light is on the way. But for now, it is quiet, and the quiet is honest. As the years pass, the horizon pushes outward a little. The lamplight grows. Yet, as expansion accelerates, some distant beacons will recede so quickly that their signals will never reach us. This is not a cause for worry. It's part of the universe's poise. The horizon asks for humility and gives wonder in return. Within the regions we can see, creation works with humble tools: cosmic dust, tiny grains of carbon, silicates, and metals floats through interstellar clouds. Each grain is small enough to vanish between your fingers, but together they change everything. Dust cools the gas around it by radiating heat away, allowing gravity to pull the cloud tighter. As the cloud condenses, pockets grow dense enough to collapse, igniting new stars. Around those newborn suns, dust grains bump and stick, rounding into pebbles, then stones, then planetesimals, the first bones of planets. Dust is also chemistry's workbench. Molecules assemble on its surfaces, simple at first, then more elaborate, a quiet preparation for climates and oceans and life. It is easy to overlook the dim parts of the nebula. It is also where futures are forged. Sometimes that dust hides the most exuberant places from simple view. In galaxies swaddled in thick clouds, optical light is swallowed, and all you might see is a dark silhouette. But dust that drinks starlight re-radiates it in infrared, which slips through the veils. With infrared eyes, those dark regions bloom, nurseries where stars are being born by the thousands, galactic hearts in the middle of growth spurts. Reading this glow lets us count the hidden birth rate, trace how galaxies fattened in their youth, and understand how the early universe brightened. It's like standing outside a house at night, windows curtained, rooms dim, and then finding the one wavelength that turns the whole interior gently visible. Trace the story backward, and you arrive at a time before dust existed at all. The first stars formed from the simplest mixture the cosmos could offer, mostly hydrogen, a little helium, and almost nothing else. They were nearly pristine, and by many models, enormous compared to typical stars now. Burning hot and fast, they made the first heavy elements in their cores and then cast them out in brilliant supernovae. Those elements, carbon, oxygen, iron, seeded the next generations of stars and built the raw material for planets and chemistry. None of those earliest giants survive today. Their lives were brief, but their ashes became the ink of everything written since. In the stillness of your room, there is something calming in that. Every breath you take carries atoms cooked in stars that shone and died before any galaxy resembled the ones we know. From those deaths also come messengers with unusual speed. Cosmic rays, charged particles, chiefly protons and nuclei, are hurled to nearly light speed by the shocks of supernova remnants, by the tangled magnetic fields near black hole jets, by the violent outskirts of galaxy clusters. When they drift into our sky and strike the upper atmosphere, they trigger cascades of secondary particles that flicker and fade long before they reach the ground. Some researchers explore whether the ionization they cause might influence the formation of cloud droplets, gently nudging weather patterns. The evidence is nuanced, the debate ongoing, and the effect, if present at all, is subtle. What matters for us tonight is the connection. Storms in distant space send traces that whisper through our air, a quiet thread linking faraway power to the tiny swirls of our weather. Deeper than weather and older than dust lies a puzzle that turns the mind soft and attentive. If the Big Bang forged matter and its mirror, antimatter, in equal amounts, why do we live in a universe made almost entirely of the former? Matter and antimatter extinguish one another on contact, leaving light behind. Yet somehow, a slight excess of matter remained just enough to build everything we see. This baryon asymmetry hints that, in the early moments, the laws of physics tilted ever so gently in favor of matter's survival. We don't yet know exactly how. There are candidates, tiny violations of certain symmetries, processes that would have unfolded in the extreme conditions of the newborn universe, but the proof is still gathering. For drifting into sleep, the comfort is this: existence itself is the residue of a cosmic near tie, a delicate remainder that became stars, planets, oceans, and you. Light carries more than color and brightness. It also carries the fingerprints of gravity's touch. As a beam passes near something massive, a galaxy, a cluster, a dark matter halo, its path bends. This gravitational lensing can be dramatic, stretching and magnifying a distant galaxy into a bright arc or even a ring. It can also be subtle, gently shearing shapes across the sky in ways only statistics can reveal. Sometimes, nature arranges for a cluster of galaxies to act as a glass, magnifying an object behind it so that our telescopes, boosted by the cosmos itself, can glimpse things otherwise too faint or too far. Staring through such lenses is like looking through a raindrop at a scene beyond the image warped. Yes, but enlarged, carrying details we could not have gathered alone. Even the oldest light we know, the faint microwave afterglow from the early universe, has been smudged in this way. On its long voyage to us, it threads through 1,000 gravitational valleys and over 1,000 hills, each one tugging the path a little. The result is a delicate pattern of distortions written on the cosmic microwave background, a record of the intervening landscape. By measuring those distortions, we can map the otherwise invisible, where dark matter piles up, how structures grew, how the web thickened. It's cartography by starlight's memory, a way to sketch the terrain of the universe without ever touching it. Put these pieces together, the reddening of light, the ladder of distances, the reach of our horizon, the craft of dust, the first star's alchemy, the quiet reign of cosmic rays, the mystery of matter's triumph, the lensing that turns gravity into a telescope, and the picture that forms is both intricate and deeply soothing. The cosmos is busy, but not frantic. It changes, but with patience. It hides much of its work, yet leaves enough clues that we can learn without rushing. And at every turn, what could have been noise becomes signal, the color of a galaxy, the pulse of a Cepheid, the hush of ancient light, the invisible tug of a mass we cannot see. You don't need to hold every term. Let them pass over you like waves on a dark shore. What remains is the sense of a universe that both reveals and protects, that opens doors slowly and keeps some corridors gently dim. Redshift is a soft dimming that tells a story. The distance ladder is a quiet staircase that feels safe underfoot. The horizon is a curtain that will lift a little with time. Dust is the dusk from which dawns are made. The first stars are sparks that donated their ash to worlds. Cosmic rays are distant fireworks whose embers cool before they touch. Antimatter's absence is a riddle folded into our very presence. Lensing is gravity's way of letting us peek. And so, while the Milky Way continues its unhurried turn and Andromeda glides toward her meeting path, the light from far places keeps arriving, shifted, bent, and carrying news. In that stream, we read the universe's diary, the calm entries written in color and curve, in ripples and threads. Stay with the rhythm of your breathing. Let it sink with that steady arrival. In, the light stretches. Out, the path bends. The next gentle truth waits where the oldest glow meets the unseen scaffold, where maps are drawn from murmurs and the dark becomes softly readable. Imagine the universe as a deep lake before dawn, perfectly still, cool, and dark. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, no points of light at all, only a thin, neutral fog of hydrogen and helium waiting in the dark. Then, almost imperceptibly at first, the horizon begins to pale. A few of the first stars spark to life, and the night takes its first breath of light. We call this the cosmic dawn. These pioneers formed from pristine clouds, simple gas with almost no heavy elements to help it cool. So many of the first stars grew massive, hot, and short-lived. They gathered in small protogalaxies, islands of matter assembling along the faint outlines seeded by tiny early ripples. Their collective glow pierced the black and, for the first time, turned the universe's darkness into a sky with candles. In their fierce hearts, these first suns forged elements beyond the original hydrogen and helium, sowing the seeds for everything richer to come. That newborn starlight did more than decorate the night. It changed the very state of space. In the earliest times, the cosmos was filled with neutral hydrogen gas, good at swallowing high-energy light and turning the universe into a kind of fog. The ultraviolet radiation from the first generations of stars and nascent galaxies began stripping electrons from those hydrogen atoms, ionizing the gas and transforming the fog into a transparent, glowing medium. This long sunrise called reionization didn't happen everywhere at once. It bubbled outward from early light sources, carving clearings that expanded and merged until the darkness gave way and light could travel freely for enormous distances. The universe went from murky to transparent, and the stage was set for the structures we now see: galaxies with lanes, clusters with cores, filaments stretching like faint highways between them. Once the lights were on, they grew brighter. There came a period billions of years ago when the universe was especially busy making stars, a tempo sometimes nicknamed cosmic high noon. Galaxies, fed by streams of gas along the filaments of the cosmic web and stirred by mergers, formed stars at rates far higher than we observe today. Think of cities with cranes on every skyline and lamps switching on in block after block. This was the era when galactic disks fattened and brightened, when clusters assembled their skylines, when the universe's economy of star formation reached its peak. As star birth surged, the chemistry of the universe deepened. Early on, the elemental palette was spare hydrogen and helium with a trace of lithium from the Big Bang. But inside stars, light elements fuse into heavier ones. Massive stars, especially, manufacture carbon, oxygen, silicon, iron, and more, and they do it quickly by cosmic standards. When such stars end their short lives, they explode as supernovae, stirring and enriching their surroundings. Gas that was once simple now carries metals. Future clouds can cool more efficiently. Smaller fragments condense into a greater variety of stars. Rocky planets can form. Atmospheres can collect. Chemistry can wander toward complexity. Over cycles of birth and death, the interstellar medium becomes a richer brew, and later generations inherit that richness. In that sense, every quiet world has an ancestry of fire. The places where this history unfolded were not arranged randomly. On the largest scales, matter settles into a cosmic web, long filaments connecting nodes where clusters grow, with wide voids between them. Gravity, guided by the faint, early blueprint, etched into the ancient light, draws material along these threads. Dark matter supplies most of the scaffolding. Ordinary gas follows the scaffold, cools in the densest spots, and builds galaxies. Over time, filaments thicken, crossroads grow into bustling clusters, and the empty spaces between them clarify the pattern, the negative space that makes the lace visible. Even in its immensity, the web looks delicate and calm, stretched like frost across a window, intricate and quiet. At the hearts of many maturing galaxies, supermassive black holes stir, When enough gas falls inward, these central engines wake and, paradoxically, brighten their surroundings, heating infalling matter until it glows and sometimes launching jets. Narrow beams of charged particles accelerated to near light speed. These jets can travel for millions of light years, injecting energy into the gas they plow through, sculpting bubbles, and gently regulating star formation. It's a feedback, not unlike a careful gardener, not erasing growth, but keeping it from running wild. The dance between galaxies and their central black holes is one of quiet influence, energy added here, gas pushed there, guiding how bright, how large, and how quickly galaxies mature. As galaxies pile into the nodes of the web, they form galaxy clusters, the largest gravitationally bound structures in the universe. A cluster can hold hundreds or thousands of galaxies, sharing one deep potential well, its interior filled with thin, blisteringly hot gas that glows in X-rays. Dark matter dominates the mass, shaping the well. Galaxies orbit like fireflies in a valley. The hot gas bathes everything in a light, too energetic for human eyes. Clusters bend, passing light strongly, acting as gravitational lenses that magnify the even more distant universe behind them. By studying clusters, their galaxies, their X-ray glow, their lensing maps, astronomers weigh the hidden matter, track cosmic growth, and test how the expansion's pace has evolved. In these densest nodes, the universe becomes legible in many overlapping alphabets. Under all this structure sits a simple geometric truth. On the largest scales we can measure, the universe is remarkably flat. Flat doesn't mean empty. It means that space, averaged over vast distances, is not curved inward like a sphere or outward like a saddle. Parallel beams of light remain parallel. Angles in huge triangles add up as expected, and the rules of straightness match Euclidean intuition. This near flatness supports the story of inflation, the early, brief episode that smoothed and stretched space so thoroughly that any initial curvature was diluted to near zero. A flat cosmos tends toward a future of continuing expansion, slowly at first, then increasingly, gently accelerated by dark energy, more room opening, more distance unfolding between very far things, all without edges or boundaries to hit. How did the universe know where to place its threads and nodes? The answer is written in the cosmic microwave background, the ancient afterglow left from when the universe first became transparent to light. Though nearly uniform, the CMB carries tiny temperature variations, ripples of only a few tens of microkelvin. Those ripples mark slight overdensities and underdensities in the early universe. Over time, gravity amplified them. Slightly denser regions gathered more matter, grew denser still, and became the seeds of galaxies and clusters. Slightly emptier regions shed matter to their neighbors and became the voids. In this way, the CMB is a blueprint, a quiet speckle pattern that foretold the lace. By mapping these minute fluctuations across the whole sky, we read off the contents of the universe, its geometry, its expansion history, a cosmos summarized in the softest grain. Of course, reading a blueprint from just one building has limits. Cosmology carries an intrinsic uncertainty called cosmic variance. We have only one universe to observe, only one sky to map. On very large scales, there are only so many independent patches to count. Statistics bump against a ceiling that no better telescope can lift. It's a gentle, humbling limit. The solution is not to wish for a second universe, but to measure more carefully, combine different kinds of data galaxies, lensing, CMB, supernovae, and let each reduce the other's ambiguities. Even then, a small, unavoidable fuzziness remains. Rather than a flaw, it's a reminder of our singular vantage. We are one set of eyes in one cosmic room, doing our best to read the wallpaper. Amid that humility, the timeline still comes into focus. Astronomers estimate cosmic ages by decoding the light of distant galaxies. A galaxy's spectrum carries the blended signatures of its stars. Young, hot stars leave one pattern. Older, cooler populations leave another. By modeling these mixtures, measuring how much starlight has reddened with age, and comparing to known stellar life cycles, we infer when the galaxy's stars formed and how its growth unfolded. Combine that with redshift, how far back in time we look, and we reconstruct a history when the first lights kindled, when star formation surged, when it settled, how quickly heavy elements accumulated, and how the web knitted itself tighter. It's not a single clock, but a choir of clocks ticking together. If you let these ideas settle, you can feel the continuity linking them. The first stars ignite, their light ionizes the fog and clears the room. Reionization opens for long-distance travel of light, and with it comes visibility. Galaxies can see and be seen across space. Star formation surges at cosmic high noon, enriching the gas with heavy elements that, grain by grain, unlock cooler clouds and more intricate outcomes: planets, rocks, oceans, perhaps mines. The web grows from tiny blueprint, ripples into filaments and clusters. Central black holes wake and guide their hosts with jets and gentle heating. Clusters pool mass into the deepest basins, lensing the background and writing maps we can read. Geometry holds flat, pointing back to inflation's smoothing hand. The oldest glow remembers the first pattern. Cosmic variance sets the soft edges of certainty, and the light of faraway cities tells us how long ago their lamps were lit. Even when the universe raced early, stars flaring hot, jets drilling outward, clusters swallowing strays, the feeling of it, at human scale, is serene. These changes unfold over millions and billions of years. They are the slow workings of a patient cosmos, the kind of pace your breath can keep. If you need a single image to cradle all of this, choose a dawn over fog. At first, a diffuse gray, then bead-like lights in the distance, then shapes pulling into focus, the roads, the rivers, the bridges, and finally a day with its own gentle rhythms. The lights that came on long ago never stop traveling. They are arriving now, quietly, through your window of time. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, no points of light at all, only a thin, neutral fog of hydrogen and helium waiting in the dark. Then, almost imperceptibly at first, the horizon begins to pale. A few of the first stars spark to life, and the night takes its first breath of light. We call this the cosmic dawn. These pioneers formed from pristine clouds, simple gas with almost no heavy elements. To help it cool, so many of the first stars grew massive, hot, and short-lived. They gathered in small protogalaxies, islands of matter assembling along the faint outlines seeded by tiny early ripples. Their collective glow pierced the black end. For the first time, turned the universe's darkness into a sky with candles. In their fierce hearts, these first suns forged elements beyond the original hydrogen and helium, sowing the seeds for everything richer to come. That newborn starlight did more than decorate the night. It changed the very state of space. In the earliest times, the cosmos was filled with neutral hydrogen gas, good at swallowing high-energy light and turning the universe into a kind of fog. The ultraviolet radiation from the first generations of stars and nascent galaxies began stripping electrons from those hydrogen atoms, ionizing the gas and transforming the fog into a transparent, glowing medium. This long sunrise, called reionization, didn't happen everywhere at once. It bubbled outward from early light sources, carving clearings that expanded and merged until the darkness gave way and light could travel freely for enormous distances. The universe went from murky to transparent, and the stage was set for the structures we now see: galaxies with lanes, clusters with cores, filaments stretching like faint highways between them. Once the lights were on, they grew brighter. There came a period, billions of years ago, when the universe was especially busy making stars, a tempo sometimes nicknamed cosmic high noon. Galaxies, fed by streams of gas along the filaments of the cosmic web and stirred by mergers, formed stars at rates far higher than we observe today. Think of cities with cranes on every skyline and lamps switching on in block after block. This was the era when galactic disks fattened and brightened, when clusters assembled their skylines, when the universe's economy of star formation reached its peak. As star birth surged, the chemistry of the universe deepened. Early on, the elemental palette was spare hydrogen and helium with a trace of lithium from the Big Bang. But inside, stars, light elements fuse into heavier ones. Massive stars, especially, manufacture carbon, oxygen, silicon, iron, and more, and they do it quickly by cosmic standards. When such stars end their short lives, they explode as supernovae, stirring and enriching their surroundings. Gas that was once simple now carries metals. Future clouds can cool more efficiently. Smaller fragments condense into a greater variety of stars. Rocky planets can form. Atmospheres can collect. Chemistry can wander toward complexity. Over cycles of birth and death, the interstellar medium becomes a richer brew, and later generations inherit that richness. In that sense, every quiet world has an ancestry of fire. The places where this history unfolded were not arranged randomly. On the largest scales, matter settles into a cosmic web, long filaments connecting nodes where clusters grow, with wide voids between them. Gravity, guided by the faint, early blueprint etched into the ancient light, draws material along these threads. Dark matter supplies most of the scaffolding. Ordinary gas follows the scaffold, cools in the densest spots, and builds galaxies. Over time, filaments thicken, crossroads grow into bustling clusters, and the empty spaces between them clarify the pattern, the negative space that makes the lace visible. Even in its immensity, the web looks delicate and calm, stretched like frost across a window, intricate and quiet. At the hearts of many maturing galaxies, supermassive black holes stir. When enough gas falls inward, these central engines wake and, paradoxically, brighten their surroundings, heating in falling matter until it glows, and sometimes launching jets, narrow beams of charged particles accelerated to near light speed. These jets can travel for millions of light years, injecting energy into the gas they plow through, sculpting bubbles and gently regulating star formation. It's a feedback not unlike a careful gardener, not erasing growth, but keeping it from running wild. The dance between galaxies and their central black holes is one of quiet influence, Energy added here, gas pushed there, guiding how bright, how large, and how quickly galaxies mature. As galaxies pile into the nodes of the web, they form galaxy clusters, the largest gravitationally bound structures in the universe. A cluster can hold hundreds or thousands of galaxies sharing one deep potential well, its interior filled with thin, blisteringly hot gas that glows in X-rays. Dark matter dominates the mass, shaping the well. Galaxies orbit like fireflies in a valley. The hot gas bathes everything in a light too energetic for human eyes. Clusters bend passing light strongly, acting as gravitational lenses that magnify the even more distant universe behind them. By studying clusters, their galaxies, their X-ray glow, their lensing maps, astronomers weigh the hidden matter, track cosmic growth, and test how the expansion's pace has evolved. In these densest nodes, the universe becomes legible in many overlapping alphabets. Under all this structure sits a simple geometric truth. On the largest scales we can measure, the universe is remarkably flat. Flat doesn't mean empty. It means that space, averaged over vast distances, is not curved inward like a sphere or outward like a saddle. Parallel beams of light remain parallel. Angles in huge triangles add up as expected, and the rules of straightness match Euclidean intuition. This near-flatness supports the story of inflation, the early, brief episode that smoothed and stretched space so thoroughly that any initial curvature was diluted to near zero. A flat cosmos tends toward a future of continuing expansion, slowly at first, then increasingly gently accelerated by dark energy, more room opening, more distance unfolding between very far things, all without edges or boundaries to hit. How did the universe know where to place its threads and nodes? The answer is written in the cosmic microwave background, the ancient afterglow left from when the universe first became transparent to light. Though nearly uniform, the CMB carries tiny temperature variations, ripples of only a few tens of microkelvin. Those ripples mark slight overdensities and underdensities in the early universe. Over time, gravity amplified them. Slightly denser regions gathered more matter, grew denser still, and became the seeds of galaxies and clusters. Slightly emptier regions shed matter to their neighbors and became the voids. In this way, the CMB is a blueprint, a quiet speckle pattern that foretold the lace. By mapping these minute fluctuations across the whole sky, we read off the contents of the universe, its geometry, its expansion history, a cosmos summarized in the softest grain. Of course, reading a blueprint from just one building has limits. Cosmology carries an intrinsic uncertainty called cosmic variance. We have only one universe to observe, only one sky to map. On very large scales, there are only so many independent patches to count. Statistics bump against a ceiling that no better telescope can lift. It's a gentle, humbling limit. The solution is not to wish for a second universe, but to measure more carefully, combine different kinds of data galaxies, lensing, CMB, supernovae, and let each reduce the other's ambiguities. Even then, a small, unavoidable fuzziness remains. Rather than a flaw, it's a reminder of our singular vantage. We are one set of eyes in one cosmic room, doing our best to read the wallpaper. Amid that humility, the timeline still comes into focus. Astronomers estimate cosmic ages by decoding the light of distant galaxies. A galaxy's spectrum carries the blended signatures of its stars. Young, hot stars leave one pattern. Older, cooler populations leave another. By modeling these mixtures, measuring how much starlight has reddened with age, and comparing to known stellar life cycles, we infer when the galaxy's stars formed and how its growth unfolded. Combine that with redshift, how far back in time we look, and we reconstruct a history when the first lights kindled, when star formation surged, when it settled, how quickly heavy elements accumulated, and how the web knitted itself tighter. It's not a single clock, but a choir of clocks ticking together. If you let these ideas settle, you can feel the continuity linking them. The first stars ignite. Their light ionizes the fog and clears the room. Reionization opens for long-distance travel of light, and with it comes visibility. Galaxies can see and be seen across space. Star formation surges at cosmic high noon, enriching the gas with heavy elements that, grain by grain, unlock cooler clouds and more intricate outcomes. Planets, rocks, oceans, perhaps mines. The web grows from tiny blueprint ripples into filaments and clusters. Central black holes wake and guide their hosts with jets and gentle heating. Clusters pool mass into the deepest basins, lensing the background and writing maps we can read. Geometry holds flat, pointing back to inflation's smoothing hand. The oldest glow remembers the first pattern. Cosmic variance sets the soft edges of certainty, and the light of faraway cities tells us how long ago their lamps were lit. Even when the universe raced early, stars flaring hot, jets drilling outward, clusters swallowing strays, the feeling of it at human scale is serene. These changes unfold over millions and billions of years. They are the slow workings of a patient cosmos, the kind of pace your breath can keep. If you need a single image to cradle all of this, choose a dawn over fog. At first a diffuse gray, then bead like lights in the distance, then shapes pulling into focus the roads, the rivers, the bridges, and finally, a day with its own gentle rhythms. The lights that came on long ago never stopped traveling. They are arriving now, quietly, through your window of time. As we drift forward, we'll keep reading what that light reveals, how the hidden scaffold holds the bright parts in place, how the expansion's soft push shapes the room, how the smallest ripples grow into the largest designs. Because light needs time to cross the growing room of space. Distant galaxies are yesterday's pages, still drifting toward us. A faint smudge billions of light years away is a snapshot from billions of years ago. Piece by piece, these old photons let us reconstruct a timeline when small protogalaxies kindled, when star birth surged, when heavy elements accumulated, and how the spacious web took shape. Astronomers read this history by comparing color, brightness, and spectral fingerprints across many distances and thus many eras. Young galaxies tend to be bluer, dustier star factories. Older ones glow redder, their massive stars long gone, their light dominated by cooler, longer-lived suns. By modeling these patterns, how stellar populations age, how metals build up, how dust reprocesses light, we estimate galaxy ages and stitch them onto the redshift map. The result is a calm, continuous storyboard. First dawn, rising star formation, a high noon of galactic growth, then a slow settling into today's gentler pace. Nothing here is rushed. It is a chronology you can breathe with. Beneath that timeline runs a quieter thread, the possibility that the early universe left behind topological scars, subtle seams in space-time itself. Some theories predict cosmic strings, ultra-thin, immensely dense filaments formed during phase transitions in the universe's first fractions of a second. Imagine hair-fine lines stretched across enormous distances, invisible except for their gravity. If such strings exist, they could create distinctive gravitational lensing signatures, tiny temperature steps in the cosmic microwave background, or a faint background of gravitational waves. We have no confirmed sightings yet, only bounds and searches, but even the hunt is soothing in its patience. It's the kind of mystery that asks nothing demanding at bedtime, a soft question left on the nightstand, linking the quantum rules of the very small to the architecture of the very large. Closer to the hearts of galaxies, another kind of relic sends its own calm signals. When supermassive black holes feed, gas spirals inward and heats to millions of degrees. That seething disk shines in X-rays hard, penetrating light that slips through dust and travels across cosmological distances. Space telescopes register these beacons as quiet flares in the dark, each one a laboratory for gravity at its most intense. By watching how the X-ray glow flickers and broadens near the event horizon, astronomers infer the spin of the black hole, the geometry of the inflow, and the ways outflows and radiation regulate star formation in the host galaxy. It's an intimate feedback loop. Central engines warm and stir their surroundings, keeping galaxies from exploding with too many new stars too fast, nudging them toward long, livable rhythms. Step out from the centers to the cold giant clouds where stars are born, and the mood changes from extreme to intricate. Inside these molecular nurseries, gas and dust are not still. They are turbulent eddies within eddies, stirred by gravity, by ancient supernova shock fronts, by the gentle pressure of starlight, and by magnetic fields threading the dark. Turbulence does two things at once. It supports clouds against collapse and compresses small pockets until gravity can take over. In those dense pockets, starlight kindles. The balance between turbulence and collapse sets a galaxy's star formation rate, the typical mass of newborn stars, and how long the nursery lasts. Understanding this balance is like understanding a good lullaby. The energy is there, but it's controlled, pulsing, never harsh. Even when stars spin down or explode, the universe keeps whispering. Pulsars, rapidly rotating neutron stars left behind by supernovae, sweep beams of radio waves through space. To a radio telescope, each pulsar is a metronome, its ticks so regular that tiny deviations reveal anything tugging on it. Companion stars, surrounding plasma, even gravitational waves passing by. Meanwhile, whole galaxies hum in radio, from synchrotron emission produced by cosmic rays spiraling along magnetic fields, to the soft line of neutral hydrogen tracing where gas gathers. In radio light, the cosmos becomes an invisible symphony. Lighthouses ticking, jets hissing, disks murmuring. Listening to it maps magnetic fields, uncovers hidden star formation, and sketches the large-scale structure that optical light alone cannot show. From those same supernovae and galactic engines comes a sparser, swifter message. Cosmic rays, charged particles flung to near light speed by shock fronts and magnetic slingshots. They wander the galaxy, finally tapping Earth's atmosphere and spawning particle showers that instruments can count. Too thin to trouble us, they're thick enough to matter to interstellar chemistry, helping ionize gas and seed reactions in cold clouds. Some studies even explore whether cosmic rays nudge cloud formation in our own sky. The verdict is still gentle and unresolved, but the connection is sweet to hold. The most distant fireworks leave the faintest glitter on our weather. While radio and X-rays carry news from specific engines, the cosmic microwave background carries the soft memory of the whole room. Its light is not only faint and ancient, it is also polarized. Its waves tend to wiggle in preferred directions. That polarization contains patterns. One pattern, E modes, mostly records how light scattered off electrons when the universe first became transparent and later during reionization. Another, subtler pattern, B modes, could carry fingerprints of primordial gravitational waves from inflation, the early burst that smoothed and stretched space. Measuring these delicate swirls is like reading ripples on a pond lit by moonlight. Every improvement in sensitivity tightens our story of how quantum jitters inflated into the seeds of the cosmic web. Even limits teach. Sometimes the absence of a signal is a boundary, drawn kindly around what is possible. We've already felt how reionization turned fog to clarity. The first galaxies and stars bathed the universe in ultraviolet light that ionized hydrogen, stripping electrons and allowing photons to roam. That transition did not flip on all at once. It crept and overlapped, bubble meeting bubble, until the windows were open. Today, by watching the faint 21-centimeter line of hydrogen red-shifted to low radio frequencies, by counting distant galaxies whose light is swallowed or spared by fog, and by reading the polarization of the microwave background, we map when those windows opened and how quickly daylight spread. Reionization is the hinge between the universe that hid its structure and the universe that displays it, a slow lifting of the curtains. As we push these measurements to greater distances, one quiet discovery keeps its gentle surprise. The universe is not only expanding, it's accelerating. Something dark energy acts like a soft, uniform pressure in space, making faraway galaxies recede faster with time. We don't yet know what dark energy is. It could be the energy of the vacuum itself. It could be a new field. It could be a sign that gravity's law is broader than our current script. What we do know is how it behaves in the data. Standard candles like Type Ia supernovae appear a touch dimmer than they would in a slowing universe. Large-scale patterns in galaxies and the microwave background line up with an expansion that has sped up in the last few billion years. For bedtime, the takeaway is gentle. The room keeps getting bigger in a steady, almost kindly way. To follow that bigness with clarity, cosmologists use a simple, soft tool, the scale factor, usually written as A. Think of it as a ruler's stretch. We set A equals 1 for today. In the past, A was smaller. In the future, it will be larger. When it doubles, the distances between faraway galaxies roughly double. When A was 1/10 of today's value, the universe was 10 times more compact. The scale factor doesn't tell you what moves where. It tells you how the grid of space expands beneath everything. Plotting at across cosmic time is like tracking your own breathing, slow, regular, with a notable, recent deepening of the exhale as dark energy takes the lead. It's a single curve that encodes inflation's first sprint, the matter-dominated coasting, and the late-time acceleration, a lullaby written as a function. All of these pieces, ages from starlight, hypothetical strings, X-rays from hot disks, turbulence in cold clouds, radio lighthouses, cosmic rays, polarized whispers from the first light, the lifting of the fog, the push of dark energy, and the ruler that stretches fit together without hurry. Imagine the cosmos as a vast archive. Distant galaxies are the earliest letters, written in young ink on coarse paper. X-rays are the marginal notes in a sharper hand near the binding. Radio waves are the low hum of the shelves themselves. Cosmic rays are a rare sprinkle of dust you can taste on your tongue. Polarization is the texture of the page, subtle, telling, constant. Dark energy is the way the room seems to widen as you walk. And the scale factor is the page number at the bottom of each sheet, letting you know where you are and how far you've come. You don't need to memorize the catalog to rest inside it. Let a few anchor thoughts float. Seeing far is seeing back. Hot hearts shine in X-rays. Cool nurseries murmur in radio. Turbulence shapes cradles. Gravity shapes cities. The first UV light opened the windows. The late-time push keeps them opening. The grid stretches. The lights arrive. The story holds together. If you like, settle on one image. A city at night, seen through time. The closest blocks are bright and quiet. Farther blocks are busier. Cranes still up, windows going in. Farther still, you see scaffolds. Then the first glow of generators. Then only surveyors' lines in the dirt. Somewhere beyond the haze, there may even be ancient seams in the ground. Old faults, like cosmic strings, that shaped the streets long before anyone walked them. Over all of it, the air expands barely felt, but enough that the far horizon keeps edging back. You stand on a balcony with a warm blanket, reading the city's history by its light. And so the timeline grows clearer without losing its calm. We read, we listen, we measure, we infer. The universe offers many voices, all softened by distance, none demanding urgency. On the largest scales, the universe can wear three simple shapes. If space is closed, like the surface of a sphere, then straight lines that start apart can slowly curve toward each other. Triangles add up to more than 180 degrees, and in the very far future, gravity might halt expansion and pull everything back together. If space is open, saddle-shaped, straight lines diverge, triangles add up to less than 180, and expansion races on forever. Between those lies flat the Euclidean calm you learned in school, where parallel lines stay parallel, and triangles behave just how you expect. Modern measurements trace the patterns in the ancient light and the arrangement of galaxies, and tell a soothing truth. On cosmic scales, space is astonishingly close to flat. Not a dome pressing in, not a saddle flinging apart. A vast, steady plain where the rules are simple enough to nap under. Flatness is not just a curiosity, it's a promise about fate. In a nearly flat cosmos, the present expansion is not secretly winding a spring toward collapse. With dark energy quietly pressing outward, the long story points toward continued widening, a room that keeps making more room, gently, age after age. Light and matter travel those straight paths, bent only where local gravity curves them near clusters, galaxies, black holes, so the grand picture remains calm and legible. Lay that geometry beside another soft principle. On the very biggest scales, the universe is homogeneous and isotropic. Homogeneous means that if you average over hundreds of millions of light years, the universe looks equally rich everywhere. No region privileged, no vast patch starved. Isotropic means that from any one point, ours included, the universe looks the same in every direction. Local neighborhoods differ. Here a cluster, there a void, but the wallpaper pattern is even. This balance of sameness and variety is what lets cosmology write universal models at all. It's the reason equations we solve here can describe galaxies 10 billion light-years away. In a sleepy sense, homogeneity and isotropy are the room's even warmth. No drafty corners, no hot spots against your cheek, just a consistent background for the mind to settle in. That even warmth revealed itself most clearly in a discovery that turned speculation into science. In 1965, while aiming to eliminate a persistent hiss in their radio antenna, Arno Penzias and Robert Wilson found a uniform microwave glow coming from every direction. That glow, the cosmic microwave background, is the afterlight from when the universe first became transparent, nearly 14 billion years ago. Its temperature is just a few degrees above absolute zero, and yet it fills all of space, as if the night carries the faintest memory of day. Later, exquisitely sensitive instruments mapped that glow and found it is not perfectly uniform after all. It carries tiny temperature ripples, fluctuations of only millionths of a degree. Those ripples are the original blueprint the slight over and underdensities that gravity later amplified into galaxies, clusters, and the long filaments that lace them together. With that blueprint in hand, we can hum the timeline like a lullaby, a first fraction of a second when space inflated and smoothed, a hot plasma age where light could not travel, recombination when electrons paired with nuclei, and the first light escaped the moment the microwave background was born, a long, quiet, dark, while no stars yet shone, the cosmic dawn, when the first lights pierced the fog, the reionization that followed, clearing the room, a brisk, middle cosmic high noon, when galaxies built stars at a great pace, and then the gentle settling to today, with expansion continuing, and dark energy slowly taking the lead. Each verse of that psalm runs long in seconds and short in sensation. The pace is always patient, because light needs time. Our observable universe is a sphere bounded by how far photons have reached us since that first transparency. As the ages pass, this horizon grows. More distant messages have time to arrive, and the sphere expands. Yet the expansion of space itself means some regions will always recede too quickly for their light to ever reach us. The horizon is therefore both a slowly widening window and an honest boundary, a reminder that this room is larger than our current view. That uncertainty is not an irritation, it's the margin that makes the page readable. Every now and then, the calm page flashes with a brief, brilliant note. Gamma ray bursts are the most energetic, short-lived events. We see millisecond to minute-long flares that, for a moment, outshine entire galaxies. Many are the death cries of massive stars collapsing into black holes. Others are born when neutron stars merge, sending ripples of gravitational waves alongside their gamma light. We catch them as distant lightning, their afterglows fading through X-ray, optical, and radio. They are not threats at bedtime, they are markers, allowing astronomers to probe extreme physics and to use the sky's most fleeting beacons to measure distances, environments, and the early universe's conditions. Threaded through all of this is a familiar effect, already part of our story. As space expands, light stretches. This cosmological redshift nudges wavelengths toward the red, softening ancient blue into present microwave glow, turning the faraway into a record of the past. Redshift is not simply a curiosity, it's a clock and a ruler we read to reconstruct how quickly the scale of the universe, 8, has grown. Plotting that scale factor across time gives us a gentle curve, an early sprint, inflation, a long, steady coasting governed by matter, and a recent deepening exhale as dark energy guides the pace. Alongside light, the universe carries a fainter, ghostlier archive, relic, neutrinos. Within the first second after the Big Bang, these nearly massless particles decoupled from the hot plasma and began streaming freely. They hardly interact with matter. They move through stars, planets, and you as if through fog. They are almost impossible to catch, but their presence still leaves fingerprints in the way structures grew, in the details of the microwave background. To detect them directly would be to hear the oldest whisper the universe still makes, the hush that began when time had barely started. The tapestry these whispers describe is not uniformly dense. The cosmic web's voids, vast, sparsely populated regions, stretching tens of millions of light years, are as important as its clusters. Voids are not entirely empty. They contain thin gas and dark matter, but their comparative absence of galaxies shapes the flow around them, letting nearby filaments stand in relief and guiding how structures evolve. In art, negative space gives form to figure. In cosmology, voids give the web its lace. Studying them helps weigh dark energy's effect, map dark matter's pull, and refine our models of the universe's growth. On smaller scales and longer timelines, galaxies change not by sudden leaps, but by slow mergers and exchanges. They drift together over billions of years, their stars interleaving, their gas clouds colliding and compressing into new starbirth, their central black holes spiraling inward and eventually coalescing. The result might be a thicker disk, a smoother ellipsoid, a more massive halo, a city remodeled rather than razed. Our own Milky Way and Andromeda are set to share this long embrace in several billion years. Nothing in that rendezvous asks for alarm. At human scales, it will be a majestic rearrangement we might only witness in diagrams and simulations, a reminder that becoming is the universe's favorite verb. Invisible forces add texture to these scenes. Magnetic fields thread galaxies end to end, faint compared to Earth's field, but vast in reach. They guide cosmic rays, shape the flow of interstellar gas, cushion shock fronts from supernovae, and help set the rules inside star-forming clouds. In radio light, we can map these fields by watching how polarized waves twist as they pass a Faraday rotation that turns invisible lines into measurable signatures. Magnetism is the quiet loom on which turbulence weaves. It doesn't dominate the pattern, but it stiffens it, giving structure and memory to otherwise fleeting motions. The universe's energetic messengers touch even biology in small, sporadic ways. Cosmic rays, those swift particles launched by supernovae and other engines, occasionally reach the ground. Most are harmless. Many are stopped high in the atmosphere. Some slip through and may cause rare mutations in living tissue. Almost always, cells repair the damage. Sometimes, the change becomes part of genetic variation, the slow currency of evolution. It is a fragile, statistical link between distant explosions and the long, quiet churn of life. As for the sky's luminous curtains, the auroras near Earth's poles, the primary artists are particles from the solar wind, guided by Earth's magnetic field. High-energy particles from beyond the sun can contribute to the theater's energy budget. But the show's main choreographer is our star. Either way, those rippling greens and reds are a nightly signature, a of how space weather brushes our world. If we rewind all the way back again to the universe's first instance, we find another soft speculation that leaves testable ripples. As the young cosmos cooled, its deep symmetries may have broken through a series of phase transitions, much like water freezing into ice. Such transitions could have produced bubble-like domains of new vacuum, expanding and colliding, imprinting faint patterns in the microwave background, or stirring backgrounds of gravitational waves. The details remain theoretical, but the idea ties together the earliest high-energy physics and the later observable sky. It's comforting that cosmology lets us look for fingerprints from times so far beyond direct reach, and that many of those searches are gentle maps of temperature, polarization, and clustering that we can read like Braille. Return, finally, to the tiny fluctuations in the ancient light, the CMB's faint speckles. They are the seeds of everything familiar, and mapping them with ever better instruments continues to refine our picture. How much ordinary matter, how much dark matter, how much dark energy, how flat the geometry, how the scale factor's curve has bent over time. Here, an unavoidable softness asserts itself. Cosmic variance. We have only one sky to measure, only so many independent regions at the largest scales. The statistics can be excellent, but never infinite. Rather than an irritation, that limit is a kindness, an honest bound to our certainty. We answer by combining clues, microwave background, galaxy surveys, lensing maps, supernova distances, letting each data set steady the others, the way a deep breath steadies the body. All these threads, flat geometry, evenness at large scales, the microwave afterglow and its ripples, the widening horizon, the lightning of gamma-ray bursts, the stretching of light, the ghost river of relic neutrinos, the silence of voids, the patience of mergers, the invisible magnetism, the rare touch of cosmic rays on life, the bubble traces of early transitions tie back into a single feeling. The universe is vast and kindly ordered, not simple, but self-consistent, not static, but unhurried. We live in a room that keeps getting bigger, under a ceiling that stays level, reading by a light that left its sources long ago but arrives right on time for sleep. If you'd like one last picture as your breathing slows, imagine a flat, starlit plain stretching in every direction. Far off, brief flashes of heat lightning blink and fade the sky's most energetic bursts. A soft wind moves through the room of space, and distant notes settle into deeper tones as light stretches with the expansion. Beneath your feet, the ground remembers ancient ripples, the oldest light's faint grain, just enough to lift gentle hills and shape wide valleys. Thin, hidden strands run under the surface, quiet magnetism guiding tiny sparks that sometimes tickle the grass. Deeper still, the earliest travelers keep flowing shy particles from the universe's first second, and over everything the map stays level, no bowl to fall into, no ridge to slide from, only space making more space. From the calm map we've drawn so far, let's lean closer to the currents that make the map move. Galaxies don't wander aimlessly. They flow along invisible gradients of gravity, slipping down the slopes carved by matter, most of it dark, into the filaments of the cosmic web. Picture leaves drifting on a slow river at night. The channel guides them toward bright clusters, while broad voids the river's quiet, open eddies let them slide past. Over billions of years, these gentle but persistent pulls choreograph encounters, trigger mergers, and set the pace of star birth. By tracing these flows, astronomers sketch the universe's grand circulation system and uncover the forces that shape growth on the widest scales. Every current has a source, and ours begins with light's first freedom. About 380,000 years after the Big Bang, the universe cooled enough for electrons to settle into atoms. Photons, until then trapped in a hot fog, decoupled and began to travel. That moment, recombination, released the cosmic microwave background, the oldest light we can see, a pale hiss now chilled to about 2.7 Kelvin above absolute zero. Before this, the cosmos was opaque. After it, space turned transparent, and light started its long, steady journey to us. In that faint glow lies a record of the room's first clear breath. Look closely, very closely, and the CMB is not perfectly smooth. It carries minute temperature ripples, mere millionths of a degree, that mark slight density differences in the young universe. Gravity amplified those tiny contrasts, drawing matter together here, letting it drain away there, until galaxies, clusters, and filaments emerged. What began as a whisper of unevenness grew patiently into the lace we see now. When scientists map these ripples with precision, they read the universe's infant conditions and the rules that let small become large. If you ask where those first ripples came from, the answer reaches back to an even earlier hush. During inflation, a brief, extraordinary swelling just after the beginning, quantum fluctuations, microscopic jitters were stretched to cosmic size. Inflation magnified the small into the seed pattern the CMB now shows. In this way, the very small handed the very large. Its blueprint, the quietest tremors, became the tides that still steer galaxies along their filaments. Those tides act locally, too. Just as our moon tugs Earth's oceans, gravitational tides from neighboring galaxies and dark matter halos stretch and reshape galactic disks. Spiral arms can lengthen or warp. Gas can be squeezed into star-forming knots. Star birth can flare, then fade. Over millions of years, close passes and long embraces leave signatures, rings, streams, asymmetries that tell the story of a galaxy's neighborhood. Evolution here is not random. It's context, the slow persuasion of gravity's surroundings. Within that context, the raw materials of stars and worlds do their quiet work. Cosmic dust, grains of carbon, silicates, and metals drifts through cold molecular clouds. Dust cools gas by radiating away heat, letting gravity take hold. Pockets collapse, and new stars kindle. Around young suns, dust gathers into disks, sticks, clumps, and climbs the ladder from pebbles to planets. On dust-grained surfaces, molecules assemble water, organics, the chemistry that someday might whisper of life. Tiny pieces, large consequences. The cosmos builds with powder and patience. To speak of distances in such a room, ordinary units feel clumsy. We borrow light's own yardstick, the light year. The distance light travels in 1 year, about 6 trillion miles, is approximately equal to 10 trillion kilometers. It turns far away into understandable. The nearest star beyond the sun sits over 4 light years away. The galaxies we admire in deep images are millions to billions of light years distant. Because light takes time to move, distance and history intertwine. A number on the page becomes a point in the past. Even as we measure, the CMB's pale glow keeps us grounded. Its 2.7 K temperature is a permanent reminder that the universe has cooled and expanded, that hot beginning softened into the vast, quiet present. In that chill, the tiny ripples we mentioned earlier continue to guide our models, test our ideas, and confirm the balance that makes the large-scale room so even. Meanwhile, the universe sends sharper notes that never quite disturb the low. Cosmic rays, high-energy particles launched by supernova shocks and black hole engines, strike our atmosphere and spark air showers, cascades of secondary particles that instruments can count. They're a constant, delicate rain, offering clues about the most energetic events elsewhere, and, on rare occasions, brushing biology with tiny changes. Most such mutations are repaired or harmless. A few join the background of variation, the slow grammar of evolution. Even here, the cosmos speaks softly. Return to the voids, and you'll find they do more than sit empty. Their low density creates gentle outward pushes on surrounding matter, shaping the flow along nearby filaments, accenting the contrast between knots and strands. By studying voids, how they expand, how they influence neighboring galaxies, astronomers weigh dark energies' role and refine the map of the web. Emptiness, in art and in space, frames the figure. At the hearts of many galaxies, supermassive black holes add their own careful edits. When they feed, they can launch jets of charged particles that spear out from millions of light years, stirring, heating, and sometimes clearing the surrounding gas. This feedback doesn't extinguish star formation so much as regulate it, preventing runaway bursts, encouraging sustainable rhythms. Jets, winds, and radiation sculpt interstellar weather. The galaxy's central engine acts less like a tyrant and more like a gardener, pruning and spacing so the grove can mature. Together, these pieces make a single, quiet picture. Currents set by ancient ripples, paths guided by dark scaffolds, tides that stretch, compress, and arrange, dust that cools and builds, light years that link distance with time, a cold glow that remembers the beginning, a rain of particles that ties our sky to distant storms, voids that define the lace, and jets that tune the growth of cities of stars. The universe is not chaos. It's a well-ventilated structure, roomy, ordered, patient. Hold one image as we drift onward, a dim, starlit river at night. Beneath the surface, unseen currents carry leaves along quiet channels. Now and then, a ripple kisses the shore, a soft shower of cosmic particles. Far off, a lighthouse flickers a distant jet on the horizon. Sometimes the river opens into a wide, calm reach, a void. Overhead, the sky keeps its even, ancient chill, and far upstream, the oldest light still hums the faint afterglow from the universe's first clearing. We'll follow the river a little farther, letting each bend arrive without hurry, and watch the final threads of the web settle into place. Now let's watch the first rooms of the universe switch on. After a long hush, cosmic dawn arrives, not with a shout, but with scattered lamps. Primordial clouds, thinned and cooled by expansion, collapse under gravity, and the earliest stars kindle in small, tentative galaxies. Their light is fierce and blue, rich in ultraviolet. It leaks into the surrounding gas, carving clearings, and for the first time, the darkness has edges. Those fledgling galaxies aren't grand, yet more like neighborhoods than cities, but their collective glow begins the universe's luminous chapter. In the same breath, their radiation starts the slow work of reionization, turning opaque fog into open air and setting the stage for everything that follows. Larger disks, thicker clusters, filaments that tighten, planets that condense, chemistry that grows adventurous. Behind that newborn glow stands an older, softer light, the cosmic microwave background. It bathes all of space with a nearly uniform chill, about 2.7 K above absolute zero, a thin, persistent afterglow from when the universe first became transparent. Its evenness is astonishing. Temperature differences are just tiny fractions of a degree across the entire sky. That near uniformity tells a simple story. The early cosmos was smooth, calm in the aggregate, with only the gentlest ripples. Those ripples, minuscule density bumps, were enough. Gravity amplified them over billions of years into galaxies, clusters, and the web between. So while cosmic dawn flips on the first local lights, the microwave background is the global backdrop, the pale ceiling that remembers the room's first clearing and the blueprint sketched into it. To arrange these scenes in order, astronomers practice a kind of cosmic archaeology. Distant galaxies are time capsules. Their light left long ago and only now arrives. By splitting that light, by reading spectral signatures and the blend of stellar colors, scientists estimate galaxy ages, when star formation began, how quickly it rose or fell, how metals accumulated in the gas. Place those ages on the redshift map, and a timeline emerges. Small groups ignite, growth accelerates, star birth peaks and then relaxes. Populations redden as massive stars burn out. Disks thicken, bulges form. This portrait is detailed not because any single measurement is perfect, but because the chorus agrees. The result is cosmic evolution told in quiet tones, a fiery start, a long adolescence of building and enriching, and the present, calmer era of maintenance and drift. All along, we hold a gentle humility, cosmic variance. We get one universe to observe, one sky to map. On the very largest scales, there are only so many independent patches to average, which means some features we see may be quirks of our single cosmic sample. This isn't a flaw in the story, it's part of its honesty. We answer by combining many kinds of evidence: microwave background, galaxy surveys, lensing, supernovae, so each data set steadies the others. A little irreducible fuzz remains, like the soft noise of a vinyl record. It doesn't obscure the music. It reminds us we're listening to the real thing. While the grand arc unfolds, subtler conversations happen closer to home. The solar wind, a steady stream of charged particles from our sun, meets incoming cosmic rays and modulates how many reach Earth's skies. During active solar years, the wind's magnetic fields swell and deflect more cosmic rays. In quieter years, more slip through, changing ionization high in the atmosphere. This dance is part of space weather, relevant to satellites, astronauts, and radio communications. It's a small thread, but it ties our local star to the broader cosmic rain. A reminder that the sun is not isolated, but bathed in, and sometimes sheltering us from the galaxy's wider weather. Zoom back to galaxies, and another invisible player comes into view: magnetic fields. Weak compared to Earth's, but vast in reach. They thread spiral arms and halos, guiding charged particles, shaping how gas flows, and lending structure to turbulence in star-forming clouds. In radiolight, we watch polarized waves twist as they pass Faraday rotation, and from that twist, we reconstruct the field's strength and direction. Magnetism isn't the loudest force in a galaxy, but it's the loom on which interstellar motion weaves. It slows some collapses, channels others, and, together with gravity and feedback from stars and black holes, sets the pace of star formation over billions of years. Return now to reionization, the slow sunrise that turned the universe transparent to ultraviolet light. Before dawn, neutral hydrogen gulped high-energy photons and kept space dark and foggy. As the first stars and galaxies lit up, their ultraviolet output ionized the hydrogen-stripping electrons, making plasma and opening windows. It didn't happen everywhere at once. Islands of clarity grew around early lights, swelled and merged until the fog relented and the universe became a place where light could travel freely. Reionization is the hinge between childhood and youth. After it, the large-scale structure we map today could reveal itself across cosmic distances. By tracking how many distant galaxies peek through at different epochs, by listening for the faint 21-centimeter murmur of hydrogen shifted to low radio frequencies, and by reading the microwave background's polarization, we piece together when the windows opened and how fast the day spread. In this same era, the smallest seeds continued to matter. The first galaxies weren't just lamps, they were workshops, forging heavier elements, stirring dust, building the first disks and halos. Their light carved the fog that had hidden them, and their gravity pulled new gas along filaments to feed further growth. In a few 100 million years, the universe shifted from a simple, neutral medium to a layered environment. Hot, ionized bubbles, cooler clumps, lanes of inflow, and the early signatures of feedback from newborn black holes. Dawn didn't merely brighten the view, it changed the rules of how matter moved and cooled. Threaded through these transformations is a possibility as slender as it is profound: cosmic strings. Some theories of the infant universe where forces unified and then separated as space cooled predict ultra-thin, ultra-dense defects in space-time, like hairline seams left from a phase change. If they exist, strings could stretch across cosmic distances, their gravity producing distinctive signatures, small lensing effects, particular patterns in the microwave background, a faint background of gravitational waves. We haven't found them, we've only learned where they're not. But the search itself bridges scales. It asks whether the quantum rules that govern the smallest things left permanent marks in the cosmic architecture we now inhabit. By now, the narrative is smooth in your hands. Cosmic dawn lights the first rooms. The microwave background is the cool, even ceiling, remembering the start. Galaxy ages chart the pace at which neighborhoods formed, enriched, and settled. Cosmic evolution is the name we give to the whole transformation forces, shaping matter, matter shaping light, light revealing history. Cosmic variance draws a courteous boundary around our certainty. Locally, the solar wind and cosmic rays exchange greetings. Globally, magnetic fields add quiet structure to gas and stars. Reionization lifts the fog and makes distance transparent. Cosmic strings remain a possibility tucked into the seams. Imagine a city just before sunrise. The sky is pale, and even the oldest light, while far neighborhoods switch on their first lamps, the universe's dawn. Street by street, the fog lifts, and long avenues appear, the filaments that guide matter's flow. You pause by a quiet substation, a magnetic hum in the wires, and far away, a faint crackle, cosmic particles checked and steered by the sun's gentle breeze. In your pocket, a map of dates shows when each district was built, with a note in the margin admitting a little natural randomness in the plan. Beneath the pavement, if you could dig deep enough, you might find an ancient seam in space-time, a relic from when the ground first set. The city is still waking, the day is patient, and everything you see belongs to one continuous, gently unfolding story. In the first blink after the beginning, the universe is thought to have undergone cosmic inflation, a brief, astonishing swelling in which space expanded exponentially. Inflation did two gentle but world-shaping things. First, it smoothed the cosmos on large scales, ironing out wrinkles so thoroughly that today, when we average over hundreds of millions of light years, the universe looks uniform and calm in every direction. Second, it took quantum jitters, tiny fluctuations in energy, and stretched them out until they became the seed pattern for everything to come. Those minuscule ripples, magnified beyond comprehension, are the origin of the faint speckles we see in the oldest light, and, in time, the reason galaxies, clusters, and filaments exist at all. In a single gesture, inflation ties the physics of the very small to the architecture of the very large. When the hot, early plasma finally cooled enough for electrons to settle into atoms, about 380,000 years after the beginning, photons were released from their tangle with matter and could at last travel freely. Those same photons are still arriving, dimmed and stretched by expansion into a uniform, microwave-warm afterglow, the cosmic microwave background. Each photon carries a little of the room's first memory, its temperature, its tiny variations, its composition. To study the CMB is to read a birth certificate, one that records both the calmness inflation left behind and the delicate irregularities that would grow into structure. The CMB doesn't shout. It whispers with exquisite precision about age, geometry, and contents, how much ordinary matter, how much dark matter, and how much dark energy the universe contains. Before scientists could listen to such soft signals, the sky offered a louder clue. A century ago, researchers noticed a mysterious radiation that grew stronger with altitude. Balloon flights by Victor Hess and others showed the effect clearly. The source was not the ground, but the sky. Thus began the story of cosmic rays, high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. They are launched by violent engines, supernova shock fronts, jets from active black holes, and they bombard Earth constantly. Today, huge arrays of detectors count their air showers. Satellites and high-altitude experiments measure their energies and compositions. Each particle is a direct courier from turbulence far away, a staccato counterpoint to the CMB's steady hum. Even as we gather messengers, we face a horizon we cannot cross. The universe has a finite age, so there's a maximum distance light has had time to reach us. That boundary, the cosmic horizon, marks the edge of the observable universe. Beyond it, more space likely stretches, perhaps endlessly. More galaxies may drift, more threads of the web may run. As time passes, the horizon slowly expands, and additional distant light makes landfall in our telescopes. Yet because space itself expands, some regions recede so swiftly that their light will never arrive. The horizon is both a growing window and a permanent limit, a soft reminder that our maps are partial and always will be. Far from frustrating, that limit is a kindness, a margin that keeps us humble while we read. Return to the CMB and look closer. The afterglow is not merely a temperature map, it is also polarized. Its waves prefer certain orientations. That polarization carries patterns. One pattern, E modes, reflects how light last scattered off electrons at recombination and again during reionization. Another, sought with extraordinary care, is B modes, a swirly pattern that could be the fingerprint of primordial gravitational waves from inflation. If detected cleanly, such a signature would be a direct echo of the universe's first split second, a delicate confirmation that quantum ripples in space-time were stretched to cosmic size. Even upper limits teach us, setting boundaries on how energetic inflation could have been. Polarization is, in effect, the texture of the oldest light, and it remembers more than brightness alone can tell. Between the afterglow and today's galaxies lies the cosmic web filaments of dark matter laced with ordinary baryonic matter, gas that can heat, cool, and form stars. Observations and simulations agree that a great deal of this ordinary matter resides in the filaments themselves as hot, diffuse gas, hard to see, but present and influential. Along these vast strands, gravity pulls material toward nodes, where clusters gather and the pace of interaction quickens. Filaments are the universe's highways. Galaxies follow them, not wandering aimlessly, but flowing along gravitational currents set by the underlying mass distribution. The result is motion with context, mergers favored at intersections, star formation modulated by the availability of inflowing gas, and large-scale coherence that makes the sky's lace intelligible. At many of those intersections lurk supermassive black holes. When fed by infalling gas, their surroundings light up across the spectrum. Sometimes they launch jets, twin lances of charged particles moving at relativistic speeds. These jets can stretch for millions of light years, heating the tenuous gas in galaxy clusters, blowing bubbles, and preventing runaway cooling that would otherwise spawn unmanageable bursts of star formation. In this way, black holes act as regulators, not destroyers, tuning the tempo of their host galaxies and of cluster cores. The largest structures we see, shocks, cavities, radiolobes, are the quiet, long-lived footprints of those brief, powerful episodes. Inflation, for its part, may have left other subtle imprints in the oldest light. The exact statistical distribution of temperature fluctuations, the way they correlate across the sky, and, perhaps, faint non-Gaussian fingerprints that betray the physics of the inflaton, the field thought to drive inflation. Each new survey of the CMB, of galaxies, of lensing, tightens the net. We may never photograph inflation directly, but its legacy is writ into the pattern of everything, the same way wind leaves dunes, whose shapes still speak after the gusts have gone. Cosmic rays, too, have a second life in our story. Beyond their dramatic origins, they interact with environments closer to home. When they enter Earth's atmosphere, they ionize molecules, launching cascades of secondary particles. Some researchers explore whether this ionization can seed cloud droplets, thereby nudging cloud cover and, indirectly, climate. The extent of the effect remains debated and likely modest compared with other drivers, but the possibility itself is graceful, a slim thread from distant explosions to the texture of our sky. Meanwhile, the solar wind, a stream of particles from our sun, modulates how many cosmic rays reach us, swelling during active periods to deflect more of them and relaxing to admit more when the sun is quiet. It is a conversation between our star and the wider galaxy, a reminder that even here, in our small neighborhood, space is not empty, but a weathered place. The currents along which galaxies move are not random canals but routes set by filaments. Over billions of years, matter drifts along these strands into deeper basins, building structure where the scaffold provides a path. Inflows feed disks, closed passages tug at arms, tides stir gas into bright knots of star formation. When two galaxies meet at a junction, their long, slow embrace can scramble orbits, grow bulges, and coax central black holes toward union. The large-scale web dictates the traffic patterns. Local physics cooling, turbulence, feedback decides how neighborhoods grow. It's urban planning by gravity, with a zoning map written in the first light. Threaded through all scales is a near ghost, the neutrino. In the first second of cosmic time, neutrinos decoupled from the plasma and streamed off nearly unimpeded, a relic background we have not yet directly detected, though its presence is felt in the CMB and in the growth of structure. Later, stars, supernovae, and black hole accretion sites became prodigious neutrino factories. These particles pass through planets as if they were fog, interacting so rarely that catching even a handful requires vast detectors buried in ice or rock. Yet each detection is a postcard from an otherwise hidden engine, a core collapse interior, a flaring disk offering details no other messenger can provide. Neutrinos tell us about conditions we cannot see, tying particle physics to astrophysics with a thread almost too fine to hold. Gather these strands, and the picture stays soothingly coherent. Inflation smooths and seeds. Photons from recombination carry the record in temperature and polarization. Cosmic rays provide a loud, particulate counter-melody, discovered a century ago and still teaching us about violent engines. The horizon frames our view, honest and slowly widening. The CMB snapshot fixes the room's first clear moment, while its polarization reaches farther back for whispers from the instant before. Filaments hold much of the baryonic matter and steer galactic motion. Black hole jets regulate and sculpt. Inflation's imprints persist in the statistics of ancient light. Cosmic rays may nudge clouds as the solar wind modulates their arrival. Neutrinos slip through the walls and deliver notes from places no light can reach. None of these pieces stand alone. Each leans on the others, and all of them together let us write a calm, consistent story across almost 14 billion years. If you want one picture to hold it all, imagine a vast, quiet, plain at first light. The ground is almost level, smooth, long ago by the universe's first expansion, with faint ripples set there by tiny tremors grown large. Above it hangs a cool, even afterglow, the oldest light so uniform you'd think it was painted, except for a delicate grain that hints at future hills and rivers. Along the plain, long causeways carry travelers of stars toward gentle hubs of many worlds, while under the surface old streams, the shy particles that pass through everything keep their ancient run. Now and then, far away, a searchlight sweeps the horizon, and sometimes a single spark lands at your feet. A distant breeze from the sun rises and falls, changing how many sparks arrive. The edge of what you can see creeps outward with the morning. Beyond it, more land surely lies, waiting to be revealed in time. And so the first breath of the universe continues to echo softly, intelligibly, through everything that followed. The room is still expanding. The pattern still holds. The signals still arrive, patient as sleep. Let the last sparks fade to embers, the far jets dim, ancient photons settle like dust in moonlight, and the web holds steady around you. The room of space stays wide and even. Distant clocks tick in colors you can't hear. None of it needs your keeping. Breathe in the long tide of space. Breathe out the slow arc of years. Somewhere a first light is still on its way. Somewhere a final wave is almost here. And between those somewheres is this body, this breath, small, warm, and safe inside a universe that moves with patient kindness. So close your eyes and let the ceiling of night grow softer. What you've learned can keep traveling without you. The threads will keep their quiet tension. The plane will keep opening, and the old afterglow will hum on. For now, let everything unneeded slip away and drift down the calm river of the dark, carried by a cosmos that never hurries and always arrives.